Now we talk about the famous example of gambler's ruin. So say there is a man, he set his eyes on getting this big amount $n, but he has only small amount $k. So say he wants to buy a CVO house which costs multi-million dollars, but he has not that much money. So his strategy is simple. He decides to gamble in a casino. And the game he plays is also simple. So it's just a coin toss, and you keep on doing this coin toss repeatedly. So if head shows up, he wins. The casino gives him $1. If tail shows up, he gives the casino $1. And the game is played till he either gets $n or he is bankrupted. Here by bankrupted we mean that he will end up with -$1, that he will owe casino $1, and at that point the casino will say that we are not going to play this game anymore. So we want to compute the probability of this person getting bankrupted. So he goes to the casino with k dollars. Now we have to use linear difference equations to solve such kind of problems, but this problem is going to be really simple and we will see how to solve it. So A is person is eventually bankrupted. So this is the event. So A is the event that person is eventually bankrupted, and B is first coin toss shows head. So we start with PK. Here K denotes the capital. So he is walking into the casino with k dollars. So PK is the starting point, is he has k dollars in his pocket. So this is relative to the capital K. So when he tosses the first coin, if it is head, his capital increases to k plus 1. In that case we will talk about P k plus 1. Else, that is if it is tail, his capital decreases to k minus 1. Now you use Bayes formula. So instead of PKA you write it like this: PKA given B, that is eventually he is bankrupted, but for now he gets a head, times probability of head plus probability eventually he is bankrupted, but right now he gets a tail, times probability of getting a tail. So B is the coin toss. So probability of B is getting a head, probability of B complement is getting a tail. So if he gets a head, so if the person is right here, if he gets a head, then his capital increases. So you end up in PK plus 1A. On the other hand, if he gets a tail, that is if he is in this portion, then his capital decreases. That is if he gets this, he gets PK minus 1A. So you write this small pk for pka, and for this equation you get pk times, so here his capital has increased by 1, times probability of head, which is half. Here his capital has decreased by 1, so you have pk minus 1 times half, which is probability of tail. And then you have boundary conditions. These are called boundary conditions. I'm just going to write a short form. Boundary conditions. That is, when the person has n dollars, the game will stop. He has made the money. He will play no further, so probability is 0. If the person has $0, then he will definitely bet one more time, because there might be a possibility that he might get a $1 and the game again starts. So notice that he is bankrupted when he owes the casino $1. So when he has $0, he can still play the game. So that is why we have the boundary conditions. So now we rearrange this equation. So let us rearrange this. So if you rearrange it, you get 2pk is equal to pk plus 1 plus pk minus 1. So you can again rearrange this equation in here. So you can say pk plus 1 minus pk is equal to pk minus 1. So we have just rearranged this equation right here. So this was for capital K, but you can have this equation for all capital levels. So you set this equal to B. So you, instead of K, so let us focus on this equation now. So we have set this to this arbitrary constant B, so we have to solve for this B first. So instead of K, you could have capital N. So this is where the game will stop. So Pn minus 1 is B. So you have all these n equations for different capital levels. Yes, you start at 0 and you end up at n. So you have all these equations. So this is equation 1. So the corresponding to 1 here, you have equation 1. Then you will have equation 2, 3, 4. You will have equation k. You will have equation k plus 1. You will have equation n minus 1 corresponding to here. You will have equation n right here. You add all of them up. If you add all of them up, then you will get a lot of cancellations. So this will cancel with this. Similarly, this will cancel with the term below. Again, this thing is going to cancel with this, and so on. Everything will cancel out. This will cancel with something here. This will cancel with something above here. P1 will also cancel out with, there will be P2 minus P1 right here equals to B with this, and so on. So there will be cancellations. What you will be left with is Pn minus P0 on the left hand side is equal to n times B. All these B's add up. So we know Pn is 0 and P0 is 1. So this is 0 minus 1. So this implies B is minus 1 by n. Now instead of adding all the equations, you could have added only these equations. So if you add these equations, you get Pk minus P0 is equal to k times B, because you're adding these first k equations. So instead of capital N, you have small k. So is equal to k times B, and B we computed like this, minus 1 by n. So this would be minus k by n. So this implies Pk is equal to 1 minus k by n, and that's what we have written here. So 1 comes from P0. So Pk is equal to P0 minus k by n, and P0 is 1 right here, because you will play the game if you have $0 for sure. So that is what we wanted to compute, pKa. This is what we wanted to compute, that the person will get eventually bankrupted if he starts with capital K. So this is our answer. This is our answer. So notice that as n goes to infinity, so if he has to get more and more money, so if he has only $500 in his pocket, but he wants to win $1 million, then n is very large compared to k. So his probability of ruin is almost 1. So as n goes to infinity, this k by n goes to 0. So pKa is 1. So that's what I've written. If n is much larger than k, the probability of bankruptcy increases. So moral of the story is, you have to have high k. So your k has to be very high compared to n. So k by n has to be pretty close to each other if you want to make a dent in your probability of winning. So if you are poor, you do not gamble. So this is again, comes to the moral questions also, that a rich man and a poor man, they both take a risk, the same risk, but the probability of poor man winning is lower than the probability of rich man winning, just by this formula, because this k is lower for a poor man, but it is higher for a rich man. So for example, a sociologist can talk about two societies, that in one society there is risk-taking culture, and in the other society the risk-taking culture is not there. Whereas a mathematician can just come in and say that, maybe one sort of society is richer than the other, so therefore probability of ruin in one society is less than the probability of ruin in another society. So that is what Gambler's Ruin is all about.